Hello everybody and welcome. Root Beer here. We're going to finish off the 2000 grade 7 Gauss paper. We're on the very last question, question 25. Of course, if you are just joining us, you can go back in the series and look at all the questions from the grade 7 Gauss for the year 2000. We've done questions 1 to 24, and we're on to the final question, question 25. Last question should be the hardest question. Although sometimes I find it's a toss-up between 24 and 25 as to which one's actually the hardest. But that's enough talk from me. How about we take a look at the question itself. Question number 25. And it's got a nice little picture to go with it. Hexagon tiling over here. A square floor is tiled, as partially shown, with a large number of regular hexagonal tiles. Okay. The tiles are colored blue or white. Okay, I would probably just call this black just because we don't have colors on these pages. That doesn't really matter. So blue and white. Each blue tile is surrounded by 6 white tiles. And each white tile is surrounded by 3 white tiles and 3 blue tiles. Okay. Ignoring part tiles, the ratio of the number of blue tiles to the number of white tiles is closest to 1 to 6, 2 to 3, 3 to 10, 1 to 4, or 1 to 2. Okay. So this is another question very similar to question number 24, which I mentioned last time. They give you certain potential answers, and if you don't have time, you can guess. For a question like this one, I would choose the lowest or one of the more extreme ratios. In this case, I'd probably choose the lowest ratio or the highest ratio. So what we've got here would be 1 to 2 or 1 to 6 would be my choices. So either A or E. Questions like this have a couple of approaches. We're going to take a look at the actual solution-based approach, so the way that someone who already knows how to do this question will approach, just to give you a little idea as to how to do a ratio question like this. But, of course, there is the sort of guess and check method that you can use, similar to the dots in question number 24, where you could try and find the number of squares inside these dots. So you can go back and look at the video. I talk about it, but you have to find the number of squares you make with these dots. And you can sit there and try and figure out as many as you can, but eventually you're going to be kind of stuck. If we don't use math and some sort of rigorous case-by-case work, we're never going to know if we have enough squares. Likewise, to solve this one, what we could do is draw bigger and bigger pictures. Set up exactly this way, where each blue tile is surrounded by 6 white tiles, and each white tile is surrounded by the 3 blue and the 3 white. And we could draw bigger and bigger and bigger ones, and eventually the ratio will become more and more clear. Now, it's certainly a way to do it, but if the ratio is 1 to 4, we might not realize that until we draw a very, very big picture, which will take up a lot of our time. And if it's 1 to 2, it might not show itself for a really, really late. We might need to have 100 or 1,000 tiles to rule out the other more difficult ratios. But that's certainly a way you can do it, and if you draw a reasonably sized one, you could probably rule out 3 of these. And just a word, when you're doing these contests, I know they discourage guessing, but if you have your choices narrowed down to 3 or 2 of the possible ones, if you can exclude 2 or 3 of the choices in your 5 multiple choices, then I would say it's appropriate to take a guess, because then your odds, your expected mark is better than the 2 marks you get for leaving it blank. Just a little piece of advice. But that's enough chit-chat. Let's actually jump in and do the question. We'll use sort of some algebra reasoning almost. Okay. So around each blue tile is 6 white tiles, and around each white tile is 3 white tiles and 3 blue tiles. Well, let's draw a copy of that picture for ourselves, and we'll use the blue, just because they're talking about blue tiles. So we'll just draw ourselves a little bit of the picture. just to remind ourselves of what's going on here. So like I say, one of the ways you could probably try and approach this question is by drawing bigger and bigger pictures, and then at random steps taking the ratio of the number of white tiles you have to the number of blue tiles you have. That is certainly eventually going to get to it, because as the number of tiles you have gets bigger and bigger, the ratio gets more and more refined. So we'll make this one blue, and we'll make this one blue, and this one blue. So here we have a white tile, and it's surrounded by 3 white tiles and 3 blue tiles. Here we have a blue tile surrounded by the 6 white tiles, just so we remember what it is that we're looking at. Okay, so for this, it's really a sort of a counting argument. Okay, we want to count up the number of white tiles in terms of how many black tiles we have, and we want to count the number of blue tiles, and we want to count the number of blue tiles we have in terms of the white tiles. So if we noted that the number of let's call the number of blue tiles B. If we knew how many blue tiles there were, then we could note that around each blue tile we have 6 white tiles. So if we're just counting the white tiles based on the blue tiles, we would get 6 times B of them. So I'd go around this blue tile and I'd say, well, there's 1 white tile, there's 2 white tiles, 3, 4, 5, 6. And then for this one, I would say, well, here's another one. So that's 7, 8, 9, 10, 11, 12. But you see, I'm counting these 2 tiles twice when I go around this blue tile and this blue tile. I'm counting these twice. So just 6 whites for each blue tile, you would get 6B white tiles. But some of these white tiles are counted twice. This is what's known as double counting. And it's something we need to sort of avoid or keep track of. So if we were to just say 6 times the number of blue tiles, we would get a ratio of 1 to 6. But that's wildly out of proportion because tiles are being counted. So this white tile in here, how many times is he going to be counted? So he's been counted twice, and then I would go, okay, this blue tile, 13, 14, 15, 16, 17, 18. So there I've counted 18 white tiles, but in actuality there's only going to be, let's finish our diagram a little bit. But in actuality, there's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of them. So we counted 18, but in fact, we only have 13. Why? Well, this tile here was counted twice because this blue tile and this blue tile both account for him. This tile and this tile, they were also counted twice. And this tile in here is counted 3 times because we have 3 blue neighbors next to him. So when I count the white tiles around this blue tile, I'm going to count 1, 2, 3, 4, 5, 6. I'll count him. Or when I count around this one, I'll count him again. And when I count around this third blue tile, I will count this square again. But we are counting some white tiles. In fact, it'll turn out that it's all white tiles. That's the problem. We need to eliminate this double counting. So if you've never seen that technique, that's something you can go learn. Double counting is, it comes up when you're counting things in combinatorics, and it's something you do need to watch out for. A lot of combinatorics problems out there are actually very tricky because you often double count. Okay. So around each blue tile, we have 6 white tiles. The other fact we know is around each white tile, we have 3 blues. And we also have 3 whites, but we're not going to do that. We're not using the whites to count the whites. We're using the blues to count the whites. We just want to know how many times each tile is going to be counted. So for each white tile, it will be counted once by each of its blue neighbors. So each white tile is counted 3 times. So if W is the number of white tiles, then each W is counted 3 times. So 3W is the same as 6B. So when we count around each white tile around a blue, so 6 whites for each blue, and this 3 comes from because there are 3 blues around each white. Each blue is going to count that white tile once. So that means each white is counted 3 times. And once we have this, which admittedly is not the most obvious thing to do, all we did was we tried to rather naively say, okay, well, if we just wanted to count the white tiles in terms of the blue tiles, what would be the stupidest and most easiest way to do it? Well, just count the white tiles around each blue tile, and that gave us 6 whites. Then when we looked at our diagram, we realized, oh, we're counting extra. And that's what spurred us to try and figure out, well, how many extra are we counting each white? Are there some whites that are counted 3 times, some whites that are only counted once? What? We investigated it, and we found that every single white tile is counted 3 extra times. And that gave us this equation. 6 white tiles for each blue tile is the same as 3 blue tiles for each white tile. Okay? So if we rearrange that, we see that the number of whites is 6 over 3 times the number of blues, which is 2 times the number of blues. So the ratio of whites to blues, number of whites, number of blues, this is the ratio that we're trying to talk about. Well, that's the same as the ratio of 2B to B. Twice the number of blues is the same as the number of the whites. Twice the blues, the ratio with that and the blues, well, we have a common factor here. So it's going to be 2 to 1. So the ratio of the whites to the blues is 2 to 1. And I just wrote this down wrong in the wrong order. It should be blues to whites. So ratio of blues to whites is 1 to 2. And that is one of the potential answers. In fact, it is the most extreme answer. It is E. Okay? So with our naive counting method, we would have come up with an answer of A. If we had been a little non-adventurous and we just tried guess and check, we probably would have come up with one of these ratios in the middle. Like maybe if you draw 6 or 9 blue tiles out here and put whites all around them, you'll get a ratio of 3 to 10 or something like that. That is a perfectly valid way to do this question. It really is. You'll slowly rule out each of the ratios. But once we use a little algebra, we assign a name to the number of blues, assign a name to the number of whites, and we start trying to count, and we realize we're counting extra, we can come up with the correct answer, which is 1 to 2. But I like this question. It rewards cleverness. I'll put the E up here. It rewards cleverness in that this is a much quicker way. In fact, I think I might have solved this quicker than question 24. This is much faster to do, to use math and assign names like B and W. It's much faster, and I would say it's actually pretty simple if you know how to do it. But you're not punished if you don't know how to do it, as long as you have the time. So if you did really well on the other questions, and you had the time to draw a bunch of big pictures for this one, you could get this one too. I like it when they do that. I think it's poor contest design when you have a question, and this was not one of them, but it's poor contest design when you have a question and there's only one way to do it, and it's only if you've heard of this very specific, very weird, triangles intersect only at this point sort of thing that is in some really old textbook that whoever made the contest probably grew up and loved that result. But if you've never heard of that, there's no way you're going to be able to figure that out on your own, and so you just sort of lost on a question like that. But that's not the case for this one. I like counting ones like this because there's a clever way to do it, and then there's usually a draw a bigger picture way to do it. And I think that's excellent. It gives everyone an equal chance, but it does reward those who are clever and those who use more mathematical and more exact reasoning. But that's it. That's the 2000 grade 7 Gauss paper in its entirety. So that's question 25. I thought that was an excellent question. I really can't say enough about it. And yeah, it's not a whole lot. I'll probably move on either to the 2008 Gauss next. Or sorry, not the 2008, the 2000 grade 8 Gauss next. Or maybe I'll jump into another one of these. Who knows, but look for the next contest video coming up shortly. And if you liked this contest and you like these series, feel free to throw a like or subscribe or leave a nice little comment down below. Did you use the picture way to do this, or did you come up with an interesting algebra way to do it, or did you come up with a brand new way that I didn't even mention? Leave a comment down below, and as always, it's been wonderful sharing math and math contests with you guys. I'll see you all in the next video.